it's very hard to improve something if you do not understand why it fails or even how it works, right? So that's where mechanistic interpretability comes in. It's a field where it's kind of neuroscience of AI. So you're basically trying to understand how a model works under the hood. And it could either be just like in general, how can a model compute arithmetic? Like what happens inside of the neurons when it computes arithmetic? Or it can be something like, why does the speech-to-text model just generate in a sequence? And then you want to find out why that happens inside of the neuron.
You and I are going to talk about something called mechanistic interpretability. You send me a link to a man named Chris Olah talking to Lex Friedman. There's like a YouTube clip of about 20 minutes. I think it's just called Mechanistic Interpretability Explained, which is a really good introduction to the topic and a bit of a deep dive into some of the complexities around it. But in simple terms, can you just talk about why, when we're working with machine learning, or more specifically with neural nets, why it's a little bit different to traditional computer programming in that we don't always know why these models are doing something or how they're doing something?
Yeah, so I think Chris Olah, a famous researcher at Anthropic, he put it very well. Like there's a misconception that we are programming the models and we're kind of putting in logic ourselves into how it's supposed to do things, while in reality, we're kind of growing it, like growing kind of a biological neural network. And every time we grow it, it's slightly different. And yeah, so we're not really in control of how these models solve things. We're letting them kind of find it out themselves through training. So the problem with it, like it works very well, like we get very strong models, but we don't really know how they work and how they arrive at an answer. We don't understand the logic that happens inside of these neurons connected to each other, how kind of it can process, for example, text in a chatbot, and how that can then answer complicated questions. And the problem with us not knowing this is that it becomes very hard to understand behaviors we do not want. Like it's very hard to improve something if you do not understand why it fails or even how it works, right? So that's where mechanistic interpretability comes in. It's a field where it's kind of neuroscience of AI. So you're basically trying to understand how a model works under the hood. And it could either be just like in general, how can a model compute arithmetic? Like what happens inside of the neurons when it computes arithmetic? Or it can be something like, why does the speech-to-text model just generate in a sequence? And then you want to find out why that happens inside of the neurons. And then the hope is that if you can identify why this misbehavior happens, that you will then be able to fix it. Or if you're able to understand like how models work in general, maybe you discover that their reasoning process inside the model is flawed, and then you can find a way of making it better. But it's very hard to improve something when you don't understand how it works. Then it becomes random shots and like very weak, vague theories of why something fails. And sometimes it works, but in most cases it doesn't. So a lot of time and efforts are like wasted because we don't know enough. So mechanistic interpretability, some people just call it interpretability because they're kind of similar, but it's a wide field, and there's many directions of how you can study these artificial neural networks. But one way of doing it is what's called circuit discovery. So what you're trying to do is you're trying to follow how the signal for, let's say, an arithmetic question, 10 plus 5. We're trying to understand how the neurons send the signal from the input all the way up to the output, which is the answer of the question. So we're kind of trying to understand the flow through all the neurons. The problem with this is it's very difficult because big models, they have billions of neurons. So you can't really just look at them, each individual neuron, to just follow it. It's impossible for a human brain, right? So that's where what's called circuit discovery is coming in. It's you're trying to narrow down this artificial neural network to only the neurons that are important for a certain task. So for example, in our 10 plus 5 arithmetic question, we're trying to isolate the neurons that are actually participating in computing this. So we want to kind of remove all connections between neurons that are irrelevant for this task. So we can basically just remove them. And then in the end, we want as few neurons as possible that still is able to kind of do this task of arithmetic. Or then you will try and kind of keep the neurons that will keep this happening, right?
Is that a common problem, the one that you're referencing there? Is
No,
that like
it's only
just a
us.
funny one?
Only us once. I think it's fixed. Um But yeah, so how do we do this? The most basic way or the first method that tried to kind of do this automatic, kind of this like narrow down the neural network to only the important neuron and the important connections between neurons. That method was doing it a very logical way. It's first looking at the first connection between neurons. It tries to remove it, and then it tried to see if the output changes. So whether instead of answering 10 plus 5 equals 15, it starts answering something else. And if nothing changes, then it concludes that this connection between neurons isn't important. So we can just remove it. And then we move on to the next one. Does the same. Next one. Same. And then it only keeps the neurons and the connections between neurons where it actually has an impact on the output. And then in the end, you will have this, what's called a circuit, which is this tiny version of the full neural network. So that's one method, but you can figure that if you have billions of neurons, this becomes extremely slow because every time you remove a neuron, you have to do a full forward pass or like one computation of the output, right? So you have to do billions of computations. So this becomes intractable for large language models. Then you have another method that's called gradient, and it's basically doing something similar, but instead of like removing a connection between neurons, it's instead just doing a tiny increase of the signal, almost infinitely small increase of the signal, and then it sees how much the output will increase in response to that tiny increase. And then the amount of increase corresponds to then how important that neuron is, like how much it influences. So if you do a tiny increase and nothing really happens in output, it's not important. And
But
then you do
why
the
is
same.
that?
Yeah.
Sorry. Yeah. Why is that? That to me sounds as slow, as expensive. You're turning it off and on versus, as you sometimes say to me, just wiggling it a little bit. Why
Yeah.
is that any faster or more efficient than the turning each node off and then back on again?
So if you were to wiggle or increase the signal a tiny bit, that would be exactly as slow as the other method. But you can compute this very efficiently with something called backpropagation. I won't explain exactly how in this interview, but it will be a long interview. But it is possible to compute this infinite small wiggle very fast. It's the same technique you use to train models. So it's a very fast method. You can do everything in one backward pass, basically. So you go the signal forward, and then you can take the signal backward, and you can compute all these kind of what's equivalent to these kind of tiny wiggles.
Yep. In a way that's not possible with the on-off method.
Yeah. The on-off method would probably be better, but you can't do it as fast. You can't do this trick the same way, at least not that we are aware of. And this is where kind of our method comes in. So the problem of both these two previous methods is that they're kind of dealing with the kind of interacting or intervening on one neuron connection at a time, right? But the problem is that there can be interactions between neurons. So imagine two kind of light switches where if just one of them are on, then the light will be on. So the light will be on, the light is on, light is on, the light is on, light is off. So the same can happen with neurons. There's no change in output if both neurons are there. There's no change in output if one of them is removed, but something will happen when both of them are removed. So this is what's called a logical OR gate. And the problem here is when we're doing our test where we're kind of just turning this one off, which seeing if it changes the output, and then we're trying to do this one alone, then both of them will seem unimportant. Like they'll seem like they don't change. If you had measured both of them at the same time, then you would have seen that they actually combine, they have an influence on the output. And the same problem with the wiggling is you can have like, if you only wiggle one of them individually, nothing really happens. But if you were to wiggle both simultaneously, then something would happen. And that's kind of what our new circuit discovery method does. It's called GIM. It's short for gradient interaction modifications. And basically it's some tricks, some hacks, you could say, where we take this gradient, this like wiggling method,
Wiggle.
and wiggle, yeah, and we're estimating how the impact would be if you were to do this on several neurons simultaneously instead of just one. It's not perfect, and I think there's still a lot of room for improvement, but it was so good that it worked that well that we actually topped now the kind of the benchmark, the leaderboard for these circuit discovery methods.
So just to summarize a little bit, so we need this mechanistic interpretability because we need to understand how and why these models are doing what they're doing. The most, let's say, sort of blunt method for doing that is just turning each node off one by one and seeing whether there's an impact on the output until you're kind of left with the consequential nodes. I think of it kind of a little bit like a Minesweeper or something. And then a slightly more kind of efficient way of doing a similar task is this field of what you called gradient methods. And importantly there, you can do it in a couple of passes. So you can do it even on the largest language models. And it's, I don't want to put words in your mouth, but it's more or less as accurate, maybe slightly less, but more or less as accurate as the on-off method.
Slightly less, because you're kind of trying to estimate what a big change would be by doing a very small one. And that's not necessarily the same. Yeah.
Gotcha. But then within that field of the gradient methods, we now have GIM, as you say. And the important difference here compared to previous methods is that you have an extra consideration for how each of the nodes are sort of interdependent on one another towards that particular output. So how affecting one might affect others, as opposed to just how it affects the end output. You say it's imperfect and there's work to do, but today, as I understand it, if anybody wanted a tool for kind of revealing how these models are working and seeing which nodes, which features, and which circuits are consequential to an output, that, as you say, according to that Hugging Face benchmark, which is probably the most objective sort of best benchmark there is, it's currently the best method.
Yeah. On the mechanistic interpretability benchmark, which was made by a lot of researchers from all different universities, it's on the top.
It's because this part of this gradient method, it's cost effective enough to be a method appropriate to even the largest models. But that almost makes it sound like that's the value of it. Am I right in saying that even if you take GIM and compare it to some of the more blunt models like the on-off, is GIM actually a more accurate method, or is it only that the on-off methods are only useful for small models? Does that make sense?
Yeah, it makes sense. So this leaderboard, it kind of evaluates these methods on a range of different models, large language models, on many different tasks. And there is a lot of variance. For some tasks, one method would be slightly better than another, while for another one would be better than another. But on average, our method is the best one. So there would be there's I think it was like one tiny GPT-2 model where this like removing things was better, while for other ones our methods was better. But in addition, ours was much faster. So there's actually some of the models that there is enough compute to kind of compute the circuits with the on-off method. So they just couldn't evaluate it even.
Maybe just to also just talk about why this matters, which you introduced at the start. But for a healthcare organization like ours, compliance and safety and trust and all these topics are obviously particularly important. So being able to explain to the best of our ability how the models are doing whatever they're doing is like paramount to us, right? And to the people that we serve, of course, it's like a huge priority. Often even like regulation requires it. But in general, when we talk about mechanistic interpretability, this is something that all sorts of organizations in this space are researching and looking into, right? If we look at that Hugging Face leaderboard that you mentioned earlier, we're probably the only healthcare company or healthcare AI focused company on there, right?
That's
who
true.
else is doing this research and who else is focused on this space?
So mechanistic interpretability, I would say the big players are Anthropic, and DeepMind also has a very good interpretability team. And then there's just a bunch of institutes at different universities. But yeah, also like Far AI, and yeah, there are a bunch of institutions doing this.
It's a big priority for a lot of kinds of organizations. Do you think it's a priority for them for the same sorts of reasons we talked about? That again, it's just in order to make these safe enough and more kind of applicable to various use cases that we need to develop a better understanding?
I think it's a mix. I know that Anthropic, there's a lot of like doomers. So there's a lot of people that fear that when we build strong enough AI, they will take over the world, and they will kind of, AI will lie to you, right? And they kind of want to find a way of looking into the parameters to make sure they're not lying and not deceiving us, and also kind of finding failure cases where they could become dangerous. So that's like one of the motivations. I think another one is just it's just much better, easier to do, to make something good if you understand how it works. I think that's the main intuition here is let us like, until now we're doing alchemy. We're just trying stuff out, and then we have some vague theories that are probably on some abstract level somewhat correct, but not really right. It's kind of like all the theories about how the Earth go around the sun, where Kepler just thought it was just some natural law that went around the sun, and that was somewhat correct. But Newton's explanation was better, whereas with gravity pushing and pulling the Earth, and that makes it go in orbit. But then Einstein updated that version of the explanation, and I think my point here is. You can have bad explanations that are not optimal, but they can still bring some value. And I think that's where kind of AI is now. But we need to kind of go deeper to get to the Einstein explanation of how it works.
Yeah. So just taking notes. So you think you're Albert Einstein in this situation?
That's my point.
Yeah. Shut that down.
Yeah.
There was at least recently talk about the efficacy, accuracy, kind of usefulness, if you will, of these large language models, at least kind of plateauing. Like we got to a point where adding parameters and adding data sets and so forth didn't seem to be creating the same kind of exponential improvements that it was doing in the early days. I don't know if that's still true. I don't know if there have been some changes in terms of how effective that approach is. But is your point, I guess, is that we can, or we with these tools, we can start to be a little bit more kind of surgical in terms of what fixes we're doing in these models, rather than, as you said at the start, just kind of like a kind of biological point of view, just letting it grow and hoping that it ends up being useful.
Yeah, I think a nice way of seeing this is so okay. You can kind of like understand how good models are in math or arithmetics from just doing like benchmarks where you ask it questions and you see how well it answers, and then you see like, oh, okay, it struggles a bit with these large numbers and stuff, but that kind of doesn't give you the full answer. Like it's not enough to just measure what goes in and out. It's also it's much more important to understand how it solves it, not like the output. So I think an example I like to use is for arithmetics. There was, for example, two different studies that have looked into how large language models solves arithmetic, and they're essentially, you would hope that they were solving it like we do, like you first add the first digits and then you take and move over to the next, to the 10th position. But that's not how they do it internally. What they're doing is they have a bunch of groups of neurons that represents like some ranges of numbers. So there would be like this group of neurons. It's like they will fire if the first number is between 9 and 14 and the other number is between 21 and 24. While this group of neurons will fire on different ranges of numbers. And then it's just like thousands of these kind of ranges of estimates. And then they will fire, right? And then because there's so many, the average of all these signals these neurons will send will get close to the correct answer. So this, and I don't know if it's true, but people say that if you have a bunch of people guessing the weight of the cow, then the average of the guess will be pretty good. And that's kind of how it seems like they are solving arithmetic. And when you know this, it's like, it's obvious then why these models are so bad at math, and like why they cannot like solve just like big numbers when they can't do it without using a calculator. I think this is kind of like what the mechanistic interpretability can help us understand, to kind of understand why it doesn't work, and then we can improve it.
they're not really doing maths. They're just very good at guessing. And there's a big
Yeah,
difference between the two, like methodically following a process versus just wisdom of the crowd's guesswork. But why would mechanistic interpretability help with that? To me, it simply reveals that that's what's going on.
yeah. And you're right about that. There aren't yet that many examples where after discovering it, they have then found a good way of fixing it. There's some on like tiny models on very specific tasks, but there haven't been like some very clear. But that's kind of a part of the research, and I think that's the next step of the technology to develop. And if I'm speculating a bit, it could be that the big AI labs that develop chatbots, that they have found some of these techniques and are not sharing it. But this is pure speculations. I've just seen that some people have hinted at it, but not saying anything. But yeah.
So, very, very cool. So the GIM approach, is that open source?
Yeah, we are open sourcing it. My colleague and collaborator Asper Christensen is working on making like something called a Python package where you can easily use it for any transformer model. And a transformer is basically the architecture that all large language models use.
So at the moment, this is a pretty big step in the field of mechanistic interpretability, especially in terms of kind of revealing what it is that's going on underneath. And now you're going to open source it so that all kinds of companies in this space are able to use it. And then the exciting next phase of this is what we're able to do once we have a better understanding of what's going on inside these models. What does that mean? How can we improve them? And what other fields of investigation open up to us?
Yeah, kind of now the way we edit models is that we try to change the training data a little bit, like the objective they're trying to do it. But it would be, I hope that, and I think a lot of other people hope, that we will get to a point where we can more specifically edit in the neurons, where we see like, okay, this is obviously a wrong thing you've learned, and then we can just change it a little bit. So models start lying less and don't swear at you or become racist. That would be cool.
That would be cool. I think it's simultaneously really kind of shocking and interesting to hear how, whether we're talking about OpenAI, Anthropic, any of the big AI labs that we all know very well, it's kind of interesting to hear that their ability to understand what's going on within these neural nets is pretty poor. It's also really kind of shocking and exciting to hear that there seems to be this kind of turning point now where this entire field of inquiry, this entire field of building and deploying these artificial intelligence systems now might be able to do what you just said, which is get a little bit more precise and be a bit more surgical in the way that the next improvements and the next generations are being built. So I think super cool, and congratulations getting on top of the list. I know that you're very ego driven and these things matter a lot to you. And yeah, well done.
True.
All right, thanks a lot, mate. Cheers.